Okay. Okay.
There's four. So you see on level. Level is right.
You want to say it? Yeah. Okay. All right. Sorry about that. Let's keep going. So Hibbard deletion. Like I said, in this case, they picked choosing the smallest element of the right subtree. In this case, it's 7. So they deleted the 6 and then they replaced it with the 7. And notice that once we replace it with 7, all the BSD properties are still maintained. So it's still a valid tree. Now we remove 4. Yeah, so they remove 4 and they place, again, similarly, place 5 up there. And notice that, again, BSD properties are still maintained. Any questions about, yeah?
So for this particular form, you would either take the smallest element of the right subtree or the largest element of the left subtree.
Yeah. This is Hibbard deletion. It's Hug has a good video about Hibbard deletion. There are 3 cases of deletions. You either have no children, 1 child, or 2 children. The case with 2 children is called Hibbard deletion. Yeah.
For deleting 6, why didn't you replace it with 5, which is the smallest on the right subtree? Because then where you would have
why didn't we replace 5? So you could, because like I said, there are 2 options. You either pick the largest of the left or the smallest of the right subtree. In this case, they just picked the smallest of the right. It's totally valid. If you picked 5, let's see, it would be more spindly like. Like notice that if you can kind of visualize it, like over here, if I would go up there, it'd be kind of spindly, but it still maintains properties of the BSD. So it still works. They just chose to make it more bushy. But yeah, good question. Any other questions, observations? All right, cool. Yeah, now we have the structure of and runtime of BSDs. So normally we're trying to keep it bushy. Bushy in this case means you fill in all the left and right children before you move on to the next height. So it's well balanced, as you can see on the left side. Spindly means you kind of just make it as tall as possible. This is something we want to avoid because notice that the spindly one has height of n and the bushy one has height of log n. And like something like quick union or weighted quick union, the fine algorithm is dependent on height. So if we have a larger height, we have a worse algorithm. So that's something to consider. Now we move on to tree traversals. So a trick that's really helpful here for tree traversals is drawing this sort of diagram. So you would start on the left of D and then kind of trace out the purple line all the way until you get to the right side of the D node. And this works for DFS traversals. Remember that DFS traversals have 3 kind of options. You have the pre-order, in-order, and post-order. And in the following slides, we'll see how drawing this sort of purple trace helps you identify the sequences for pre, in, and post-order. So for pre-order, it's associated with the left. So again, we want to draw this kind of diagram or this purple trace. And then every time we see the left of a node, we'll put it in our pre-order sequence. So as such, we start from the left to D. So D is first in our sequence. Then the next left of the node we see is B, then A, then C. Then we see the left of F, E, G, and then we're done. Any questions on this? Because the other traversals are basically just the same thing. And again, these will also be posted on the egg. So yeah, in order, again, same thing, but instead of looking on the left, we want to look for any time we see the purple trace hit the bottom of a node, we put that in our sequence. So here, we still start from the left of D, but the first time we see the bottom of a node is at A. So that's why we go A, then we go B, C, D, E, F, G. Any questions on in order? Okay. Last one, post order. Again, same thing, just look at the right side of the node. Yeah, that was traversals. Yeah. Mm-hmm. So again, you're trying to trace this. You start from the left of D, and then you kind of trace the pattern all the way until you get to the right of D. And then for post order, which is associated with the right, anytime you hit the right of a node, you put that in the sequence. So notice that if we start from D, we trace all the way here. The first time we hit the right of a node is A. So A is the first element in our post order traversals. Then we hit C, then we hit B, then we hit E, G, and F, and then D. And then respectively for pre and post, you go left and under. Any questions about how this like trick works? Okay. If not, I'll move on to the next section.
Okay, so next we're going to be talking about B trees and LLRBs. And this section is kind of motivated by this underlying question, how do we maximize bushiness? So the thing with BSTs is that, like, as we saw earlier, they can either become really spindly or they can be bushy. And so we kind of want to avoid spindly trees because then the runtime becomes theta n and they're not as effective. And so this brings us to the idea of the B tree. And so for any node in a B tree, we have a limit L for the number of values stuffed in a node. And so each node can have at most L plus 1 children. And I think the most common limit we'll see is L equals 2. So that structure is known as a 2-3 tree, but you might also see something like a 2-3-4 tree. And so essentially the way that B trees work is that if any node exceeds L values in it, we want to promote the middle value to its parent node. And if the node is a root, the middle value becomes a new root and left and right are its children. And so shown here, this is just like an example of a valid B tree with L equals 2. Again, that's a 2-3 tree. And so using that tree, we can kind of just practice going through what insertion looks like. And so if we were to first start off by inserting 9, we would kind of do the same process as a BST where everything to the left is less than, everything to the right is greater than. So starting 9 is less than 17, so we go to the left, and then we go to the left of 13. 9 is greater than 5, so we'll go ahead and stuff 9 in the same node as 5, but to the right of it. And this still is a valid B tree. And then going on, let's now insert 26. So we follow the same rules to go ahead and insert 26 all the way to the right because it's the greatest node. But now we have this node that has 3 values in it, which violates our limit of 2 values per node. So we're going to go ahead and promote the middle value and bring it up to the next level. So 25 is going to move up, and now it's in the same node as 21 and 23. But again, this violates that previous condition we had. So we're going to once again promote 23 up to 17. And you can see here that 23, everything that was to the left of 23, so 21, 19, and 22, that's going to become our new middle child of this 17 and 23 node.
Why couldn't you just make 26 a child of 24, 25?
Make like over here. So that just kind of goes back to our property of like B trees as a whole is that we want to keep them as bushy as possible. And so if we were to make 26 a child, we would just be introducing another level. Yeah. Any other questions? Okay, I'll go ahead and move on then. And so how do we actually implement B trees? The answer is that B trees are kind of complicated to write out in code sometimes because like 2-3 tree is maybe not as bad, but if you have a 2-3-4 tree, you have a lot of different cases. What if a node has 2 children, 3 children, 4 children? Just kind of annoying to type out. So instead, we introduced the idea of a left-leaning red-black tree known as an LLRB. And so these are going to be based off of 2-3 trees specifically. And so here are some properties. If we want to represent the 2-3 B tree, we imagine a binary search tree. And we represent nodes with more than one value as separate nodes with a red link. And so the left-leaning part of LLRB just means that all valid red links should be to the left in a valid LLRB. And so the way we actually go about inserting stuff in an LLRB is that we insert all nodes first with red links, and then later we correct the tree. And so here you can see, like, on the left, this red link just represents that 13 and 17 are stuffed into the same node. Okay, so LLRBs have three main operations. I would say, like, this is really important. Definitely know these, maybe put them on your cheat sheet too. So if both left and right child nodes are red, this violates the fact that we can only have one red link. So we're going to go ahead and institute a color flip on the parent node. If our right child node is red, that violates the left leaning part. So we're going to rotate left 3. And so I kind of like to think about rotating left or rotating right as like a pulley. So if you rotate 3 left, then everything else will get dragged down. And same thing with rotate right. You want to rotate 4 right in this case. And you would use rotate right if the left child node and its left child are both red. So basically, if you have 2 red nodes in a row. Okay, for the sake of time, I'm going to skip these 2 examples, but we'll still be doing a problem that kind of goes over the same thing. Okay, so this is spring 2019 midterm 2. Just take like a minute, discuss with the people around you what you think.
I think it's, yeah, they're so sensitive. Oh, I think it's this thing. I think it should be fine.
Yeah.
It's fine.
Just don't touch it.
Yeah.
So yeah, so it's red towards the left, the right, the right, fix it, then you rotate 13 to the left. Yeah, 13 like that. And we read it, you still keep the left thing here, but that there's still a problem. So that. Oh, it's on the wrong side. No, I can't.
Okay, so let's go ahead and come back and discuss this question. Does anyone have any ideas what it might be? Yeah.
To rotate left on 13.
Yeah. So basically, we're going to insert 15 in as a red link. And remember, even though we technically can't have right-leaning links, we want to insert all new values in as red links. So this is why we have the operations once you insert the link in. And so because we can't have a red-leaning right link, we're going to rotate 13 left. And now we have a valid LLRB. Okay, and then this is the next question. So starting from the LLRB above without adding 15, what operations will we need to complete if we add the value 40? And so here, this is just like what we're starting out with, and we can just go through this problem together, and you guys can just say what you think we need. So first, we're going to go ahead and insert 40 in as a right-leaning link.
First, you have to rotate 39 left.
Yeah, so I heard rotate 39 left.
Yeah, because the problem is you have 2 red links.
Okay, so what do we think will happen next?
Yes.
Yes, so we have 2 red links in a row, which we can't have. So we're going to rotate 43 right. Yeah. And now we have 2 red links, which again, that's not allowed. So we're going to go ahead and color flip 40.
It's all black.
Yeah. And last, what is the last operation we're going to do? Yeah. So we can't have 2 red links. So we're going to color flip 25. And you'll notice this actually is basically just a BST. So yeah, you don't always necessarily need to have red links. It's just that if there are red links, they're always going to be to the left. That's the defining characteristic of an LLRB. So this is the answer to that question. They might do something like this where not all of the lines will necessarily be filled in. So just kind of know that and just be confident in what you're doing. Any questions on that? Okay. Last part is we just want to draw the 2-3 tree corresponding to the LLRB from part A. So I already went ahead and drew it out, but you can just see like visually the red link, once again, corresponds to a Steph node. And so I would also just make sure you're confident with kind of going between the two, knowing how to draw out both, not necessarily just 2-3 tree, not necessarily just LLRB. And yeah, I think for this section, just as long as you know the invariance of both trees as well as the different operations and practice that a couple of times, you're pretty good. Yeah, any questions? Okay, I'll go ahead and move on to the next section then.
The last advice I'd probably give for the previous topic was that I guess like the most important things for 2-3s and LRBs that will come in handy is like just knowing how to generalize the 2-3 tree helps a lot. If you remember with our asymptotic analysis problem, the branching factor was kind of consistent as we traverse the tree. Same thing happens with 2-3 trees. So a common question could be like, well, how many nodes or how many values is possible if I have a 2-3 tree that has height of like 10, for example, right? You can't draw out that. It's going to be like thousands and thousands of nodes, but you can use some arithmetic to generalize that.
Now we'll be moving on to graph traversals and algorithms. So just like we learned about tree traversals, there's also graph traversals. And we have a DFS for graphs as well as trees. So depth first search is the idea of exploring a neighbor's entire subgraph before moving on to the next neighbor. So basically, if we're starting with like your root node, in this case, let's say we're starting at 0, we want to we have to explore all of 0's children. DFS is like a recursive algorithm, meaning that we call DFS on each child. So like if we were exploring 1 first, we would have to explore all the children of 1 before moving on to the next child of 0. So you're going as deep as possible. So you would go like 0, 1, and then 2, and then 5. And then if you were breaking ties from least to greatest, you could do like 3, and then 6. Yes.
Is there a tiebreaker?
So the tiebreaker is usually like given to you on the exams, like what kind of tiebreaker they're going to be using. So there's no like general tiebreaker. In these slides, I'll be using like least to greatest. Yeah. And then that was depth first search. And then now we have breadth first search. So breadth first search traverses a graph in order of closest distance to starting point to furthest distance to starting point. So yeah, in this example, ties are broken by least to greatest. So let's say our starting point is 0. We would have to first explore all the children that are like a distance of 1 away from 0. So that would just be 1. So then we have 0, 1. And then we'd have to explore, we would start with everything that's 1 away from 0. So like we only have one object, that's 1. Then we'd explore everything that's 2 away from 0 using that one. So all of the children of 1. So then we have 2 and 4. And then now both 2 and 4 are 2 away from 0. So then there's a tiebreaker. Which one do we do first? So I just used least to greatest. So we start with 2. And then we explore like the children of 2, which is 5. So then we add 5. And then now we go back to 4 and we explore the child of 4, which is 3. So we have 3. And then after that, 3 has no children. 5 has 1 child. So, 5 has 2 children. So then we explore 6 because least to greatest. And then 8. And then lastly, we explore 7. So this is breadth first search. We're basically going in order of shortest distance to largest distance. So comparison of DFS and BFS. So I didn't put runtime on the slide, but runtime is V plus 2E. Because at max, you're considering all the vertices once and all the edges twice. And the reason for this is because each edge is connected to 2 vertices. So when we're exploring each vertices, we can't explore that edge once. So each edge is explored max twice. So does one give better results? So BFS is a 2-for-1 deal because you get the shortest paths. Because we're going from distance of least distance to greatest distance, we get the shortest paths always for BFS. But in terms of time efficiency, both of them take the same amount of time. Both of them are like around V plus E. So yeah, that's your comparison. And then BFS just gives you the shortest paths. However, BFS doesn't account for edge weights, which we'll talk about later. We also have space efficiency. Is one more efficient than the other? I'm not sure how important this is for this class, but it might be more important in like 61C, but like when we're considering how much space you take when you're running DFS and BFS, DFS is worse for spindly graphs. So when we're like having a spindly graph, we need to go as deep as possible. We need to explore all of the children before moving on to the next child. So the entire subgraph of a child before moving on to the next child. So your call stack gets very deep with a lot of recursive calls, and you need theta v memory. And then BFS is worse for absurdly bushy graphs. So if you have a really bushy graph, the further you're spreading out, we have more and more children that are an equal distance away from the root. So your queue gets really large, and in your worst case, your queue will require theta v memory. And the implementations for this class, you generally have to spend theta v memory anyway to track dist2 and edge2 arrays. Yeah, I think this is a little bit of extra information. But now let's move on to Dijkstra's algorithm. So Dijkstra's algorithm is a shortest paths algorithm that accounts for edge weights. So in BFS, we only considered like how many edges away you were from the starting point. In Dijkstra's, we're also considering edge weights. So we want to find the shortest paths considering the sum of the edge weights from the starting point. So the way Dijkstra's algorithm works is it finds the shortest path between a chosen source node to every other node in the graph. And the data structure that is used for this is a priority queue. And this orders vertices based on their distance from the root node. So objects that are closest to the root node have the highest priority and are tackled first. And to keep track of progress, it is helpful to have a table that measures the distances / edges visited from each vertex. And yeah, I think this will make more sense in an example. So let's run an example of Dijkstra's. So in this case, we're running Dijkstra starting from source node A. We have our graph here, and we see that we have our priority queue. All of the distances automatically start with infinity. So they're infinity away from the source node, but we've gone one step ahead and we've changed the distance from A to itself to be 0. So then now we know that the object with the least distance to A is A. So we can tackle it first and remove it from the priority queue. And now we have to examine all of the children of A. And if we have a distance that is shorter than infinity, we can update it, or shorter than the value already in the priority queue, we can update it. So the two children of A are B and D, and 6 is less than infinity. So B's value gets updated to 6, and 1 is less than infinity, so D's value gets updated to 1. And then you continue to have this be in order of least to greatest in your priority queue. So now we tackle D. And the reason for this is because if we went in a different order, we would get a longer path. We wouldn't get the shortest path. So to make sure we get the shortest path, we have to go from least to greatest. So then next we would tackle D, and we would look at all the children of D. And we would add the edge weights to what we already have. So let's see, D has a child B, that's 3. 3 is less than 6. So B's value would be updated to 3. And then D has a child E, and 1 plus 1 is 2. So then 2 is less than infinity, so E's value will be updated to 2. And then, okay, after that, now E is the the shortest distance from A in the priority queue, so we tackle E next. E's children are B and C. So 2 plus 2 is 4. 4 is greater than 3. We leave B the same as it is. 4 plus 5 is 9. 9 is less than infinity. We update C's distance from infinity to 9. And then we move E out. And then I didn't talk about it, but we're also updating our dist2 and edge2 array. So the dist2 array is the same as what we're doing in the priority queue. Our edge2 is we keep track of which edge we came before. So every time we change the value in the priority queue, we also have to change our edge2 array. And then our visited array is just our visited table is just the order in which we're visiting nodes. So we visited A first, we visited D second, E third. But yeah, I might be going too fast. Feel free to interrupt if there's questions. But anyway, we're on B now. So B is the least distance from A in the priority queue. We explore all the children of B. C is 5 away from B. 5 plus 3 is 8. 8 is greater than 7. We don't update C. And then everything else has already been visited. And then lastly, we do C. C has no children, so we can just leave it as it is. And the priority queue is empty. We have visited all nodes. And this is a typo. So this is supposed to be the shortest path to C. It should say A, D, E, C. And we can get that is if we look at our vertex C, we want to find the shortest path from A to C. We can look at our edge 2 array. So the edge 2C is E, the edge 2E is D, the edge 2D is A, and yeah, that's how we get our shortest path. So let me know if there's any questions. Another person will be doing practice problems and more algorithms. Yes, question. Yes, the visited is just the order in which we're visiting the nodes. So we started with A, the order in which we're taking things out of the priority queue. So we started with A, then we went to D, etc. Yes.
What if 2 points are equidistant? So if A to B was also 3 and A to D to B is also 3, what would happen then?
I think it's just whichever one is first. So we start at infinity and then we update it from infinity to 3. And then if it's equal, we don't bother updating it. We just leave it as it is. So whichever path is discovered first, that's the shortest will be that path. And then the second one, it'll just, you won't care about it. Yeah.
How do we get the shortest path from C to A using the edge2?
Yes,
Just go over that, please.
So yes, so we go to our vertex C and we see that the edge 2C is E. And then we go to our vertex E and we see that the edge 2E is D. And then we go to the vertex D and we see that the edge to D is A. So then now we have our paths from A to C, which is the shortest. So A, D, E, C. Yeah, it doesn't include B. That's a typo. It's fixed on the actual slides. Any other questions? Questions? Yes.
Can you go over what's the fringe for this thing? Is that the priority queue?
I think it's the same thing, right?
Yes, the fringe is going to be the priority queue for the algorithm.
Okay, and how do you, so if the priority queue is like a main heap, right? How do you keep track of both the distance and the node? Right, because you have to keep track of the distance up to that node, but then also the actual node.
Usually you just write as a subscript on top of the distance. I believe the distance to array is going to be think about a horizontal array. You have a split in the middle. You have the node subscript on top. Below it, you have the distance. So if it's the first node A will have a distance of 0 from itself, correct? Then for the following nodes, as you go to the right of the array, like B, C, D, E, you'll write below those characters that. What is that node's distance from the source?
Okay.
Yeah, and then priority queue helps you keep track of that as well, because you'll be kind of erasing them and rewriting them as you go along the graph.
Okay, so and then you sort based on the things on the bottom, right? Because you're sorting based on this, or it's minimum at the front.
For the priority, the fringe, yes, you'll be putting the minimum in the front because you want to evaluate those first.
Okay, so it doesn't have to be a heap then, right? It can be a list.
Yeah, it can be, yeah.
Let's say use Djikstra to find the shortest path from B to C. How would you show? So you rank Djikstra. How would you show that the shortest path is A?
So if we had a question like that, what I would do is I would write out the vertex, dis2, edge2, and visited columns like myself, and then I would just run Dijkstra's. And then the way you would find the shortest path is you would look at the edge2 array. So you would go to see what is the edge to C, which is E, and what is the edge to E, that's D. What is the edge to D, that's A. You have your shortest path. Does that make sense? So you just run the algorithm, you write that out, and you just do it mentally or manually.
Yeah, the edge to array is supposed to you want to find out A to D, what's the shortest path. Well, say you run Dijkstra, you're finished with it. Now you have to answer the question, right? You go to the D on edge 2 column, go to the D, then you just trace back. Exactly, until you reach the origin. You can do it visually, of course, but they're not going to give you a nice, clean visual. They're going to make it as complicated as possible, probably. So that's why the edge 2 array will help you out.
All right. Well, thank you all for staying. I know we've bombarded you with a lot of information, but we have 2 more questions, I think, for this topic about graphs and Dijkstra's. I'm giving you the answer right now accidentally, but why don't you guys take a minute and try to work this out is pretty much just running DFS and then DFS pre-order, DFS post-order, and then thinking about like how many edges we have to add to the graph on the left if we want a pre-order of 1, 2, 3, 4, 5, 6, 7, 8. So yeah, I'll give you guys a minute. Just feel free to talk with one another, and then we'll reconvene.
Next time.
Starting from 7, the final one is going to be 6.
All right, let's reconvene real quick. Just for the sake of time. Can anyone, or does anyone want to tell me what they got for, I guess, question A? 6? Yeah. So I think you're right. Yeah. So if we run BFS from vertex 7 here, BFS, remember, is we're going to visit nodes in like increasing order of links from the source, right? So we're going to visit 7 first, and then we're going to visit all nodes that are 1 link away. So that's going to be this 1, 3, and 5. And then we're going to visit nodes that are 2 links away from 7, which is going to be the 4, right? And then we just do 3 links away from 7, which is 2 and 8. And then lastly, 4 links away. And as a result, that's why we get 6. Any questions regarding this question? Okay, what about B? So we want the pre-order of A, or DFS pre-order of 84265173. And we assume that ties are broken numerically. Does anyone want to tell me what they got or not? So DFS pre-order is just like the number of, or like the order of DFS calls that we do, okay? So if you're given a question like this, you could just honestly run DFS on every node that they give you. But because we're doing DFS pre-order, you could just think of it as like the order that we're trying to call, right? So if we do DFS of 8, we first go to this node 8, and then we write down 8, right? Then we call DFS of its neighbor, which is going to be 4. Sorry. So then the next node is going to be 4. And then we have, once we're at the node 4, we look at, it has 2 neighbors, right? It has 2 and 5. But we want to break ties numerically. So we actually look at its first neighbor of 2 first, right? So then we go to DFS of 2. And then when we're at 2, we look at all its neighbors. We look at 4, but that's already marked as visited. So then we look at 6, and that gives us 6, right? Then we call DFS of 6, but once we get to DFS of 6, we actually just don't have any neighbors, so we start recursing back. And that recursing back is the post order, which is going to be that question C. But for now, we just won't pay attention to that. But eventually, we get back to 4, and then we call DFS on 4 again, or not call DFS 4. We go back to the frame of DFS of 4, and then we look at the neighbor of 5. We do this so on and so forth, and eventually you'll get that the pre-order will be 84265173, and we call it on DFS of 8. I know that's a lot, but yeah, are there any questions? Yeah. Yeah, it's a good question. So the question is, what does assuming ties are broken numerically mean? It's like if we're visiting a node and it has, the best way I could explain it is if we go to DFS of 4, like let's say we're at this node 4, right? It has 2 neighbors. It has a neighbor of node 2 and has a neighbor of node 5. We're going to always visit 2 first if we're breaking ties numerically, because it means that we want to select the node with the lowest value between the two. Yeah, just the lowest. But we could also, like if it didn't say break ties numerically, you could also go to 5 first from 4. Does that make sense? Yeah.
So it's two questions. First, does DFS for graphs also have a pre-order and post-order version?
No, BFS does not. Yeah.
And then for DFS for graphs, for pre-order, there's almost always going to be just one, right? Because it has to start at that value.
Pre-order always has one.
One answer.
I think if they don't say assumed ties are broken numerically, it could actually have unique, or it could have a different value, right? So like in this case, because we say we're breaking ties by always selecting the smaller value, then yeah, we only have one pre-order, which is 84265. Because whenever we get to this 4 node, we're picking the smaller value. But like if they didn't have that like assumption, then you could also say 8452, or sorry, 84573, so on and so forth.
Right. What I meant, like, so that order is only possible by one starting vertex. Right?
That order is only possible. Yeah.
And then post order, then it's like the first value returned, right? So you go all the way to the.
Yes, it's the first value turn. You have to call all the DFSs until it reaches the end, when like either you don't have any, that you visit all of the neighbors already or has no neighbors. And then the post order is when you recurse. Yeah. Yeah. A again, yes. So we're going to run BFS, and you can think of BFS as just visiting the nodes that like we're going to visit nodes in increasing order of links to the source, if that makes sense. So like, for instance, if we start from 7 here, we're going to first visit all nodes that are 1 link away. So what are the nodes that are 1 link away? It's this 1 here, this 5 here, and this 3. So we go 7, 1, 3, 5. And then we now visit nodes that are 2 links away. So 2 links away from 7 are going to be just this 4 here. So then we do 7, 1, 3, 5, 4. And then once we get to this 4th node, or sorry, I'll just say, then we visit links that are 3 links away. So 3 links away are just going to be this node 2 and this node 8. And then lastly, the 6th node is 4 links away. And that's why 6 is going to be the last node. Yeah. Okay. Just for the sake of time, I'm going to just go over, or like, we're going to move on to the next section. But if you want like better in-depth explanations, I've included this video explanation walkthrough from the 61B core staff that goes over this problem, and it has like the diagrams and stuff. Yep. And likewise, there is a shortest paths program that we can do, but Dijkstra's kind of takes a while to run. So once again, their solutions explanation is going to be on this link here. But we're just going to breeze by this just because we have another topic to cover for like these graph algorithms. Okay. So the last graph algorithm that we'll talk about for this midterm review is this thing called minimum spanning trees. Okay. So let's just go over like some brief definition real quick. Is basically, before we talk about minimum spanning trees, I'm going to break it up, right? We're going to talk about spanning trees only. So if we're given an undirected graph, meaning there's no like, there's no direction, right? A spanning tree is just a subgraph that has these 3 properties. It's connected, it contains no cycles, and all the vertices are included. Okay, what does this actually look like, right? So I'm going to give you a couple examples of what these spanning trees are. Here's the first example where we have all the nodes that are connected. So there's a path between every pair of vertices, right? There's no cycle here. And you can see that the tree itself contains all these vertices. All vertices are included in this tree. And something just to note is that the total weight here is we just add up all the edges together and we get 16, right? Here's another example of a spanning tree. It's still a spanning tree, but it's now different. Now the total weight is 12. But as you can still see, it's a spanning tree because all the nodes are connected. There's no cycles in this tree. And every vertex is included in this tree. Okay. And then just to like kind of beat it into your brain, here's another example of this spanning tree. But now the total weight is 11. But why does this all matter, right? Like, why do we care? Well, the minimum spanning tree is just the spanning tree that has the total minimum weight. So if you add up all the edges together, all the weights together, it should give you the smallest total weight. And like in the real world example, like a problem like this might come up if, say, like you're, PG&E or like a power company, and you want to connect up all cities using the least amount of wiring, right? So in that case, you would want to find the minimum spanning tree so you could reduce your costs, right? You want to connect all the cities up with just the minimum amount of wire. Okay. Are there any questions regarding what an MST is, spanning tree, these definitions, so on? Yeah. Yeah. Yeah, that is a good point. I was thinking about that when I was putting up this presentation. I feel like you're right, but like I included that connected and all vertices as two separate things just because Hug has put it to. But like, yeah, I think intuitively it kind of makes sense that if all vertices are included, then there should be a path between every pair of vertices. Yeah. Any other questions? Yeah. I'll show you in just a bit. Yeah, but yeah. Any other questions? Okay. So yeah, it was the slide right here. I think the minimum spanning tree that for this question is actually the one right here, where like you add up all the values here, it's going to be 8. Yeah. Okay. Just one last little thing before we go over the algorithms. All the algorithms that we're going to cover with this MST are going to be essentially, be carried by this property. Essentially, this cut property is the thing that's going to be, is the reason why these algorithms work. So what is a cut? Well, a cut on the slide, it says, an assignment of a graph's nodes to two non-empty sets. What I like to think about it is like you're just arranging these nodes into two separate groups, right? Into two different groups. So for instance, in this cut, this is one example of a cut where we're just placing the top 3 nodes into this green group and then the bottom 2 nodes in this yellow group. Okay. Yeah.
Then the number of nodes in each set be completely off the middle. Like here you have 5, so you have 2 and 3. But could it be 1 and 4?
It could be 1 and 4.
What 0 and 5?
It could.
That wouldn't do
it wouldn't. It would violate the definition of non-empty sets. So that, like these groups actually have to at least have one item in there for it to be a valid cut. But yeah, good question. Essentially, yeah, a cut is just you're assigning these nodes into two different groups. And then a crossing edge is simply an edge that crosses between two of these groups, right? So for instance, in this diagram here, the edges that are red, they are all crossing edges because they're crossing from the yellow to the green. Does that make sense? Once again, crossing edges are the ones that are crossing edges are the edges that cross between two separate groups. So in this case, the edges that go from the green to the yellow. Oh, yeah. What's up?
Why is the top edge red if it's actually green and green?
That is a typo. Good look. Yeah, I didn't actually notice that, but yeah, that is a typo. So the one right here should actually just be, it should not be a crossing edge. Yeah.
The one that green to yellow could also be a crossing.
The one from the green to yellow. Yeah, so this one should also be a crossing edge. Yeah. Good looks. Yeah, I didn't double check this, but yeah. I also have 2 more examples. Hopefully this kind of solidifies it more. Once again, this is another cut. All the nodes on the left are in the yellow. All the nodes on the right are in the green. And I think this one should be correct. Like all these red edges are crossing edges. And then lastly, just to give you one last, beat it into your brain type of thing, this is another valid cut. And then all of these edges are the crossing edges, going from one set to the other set. Okay. Any questions regarding this? Okay, so well, why does the cut property even matter? Well, there's this thing in lecture that Hug says, well, it's pretty much the cut property. It says, given any cut that you have, the smallest crossing edge is actually going to be a part of that minimum spanning tree. Okay, so just as an example, let's say we add all these weights to these edges, and let's say we have this cut from the from the last example. What the cut property says is the smallest or the lightest crossing edge is going to be in this minimum spanning tree. So the smallest crossing edge is going to be this one right here, right? With this value of 1. And because of the cut property, this is actually going to be a part of our MST. And this property is going to be the underlining, I guess, pattern that we'll see in these next two algorithms. Okay. Yeah.
Like in this example, like the two yellow nodes, they're not like directly connected.
Yeah, it doesn't have to be directly connected. It could just be like, it could be arbitrary randomly. Yeah, so you could have one algorithm that is, if you want to find the minimum spanning tree, just keep making these cuts randomly and then see, whether the crossing edge is already a part of the MST. If not, just add it. But then that might not be a great algorithm because it's just really random, right? Like it could take a while for it to actually finish and stuff. We don't really, I guess it seems a little jank, right? To just always, it's kind of magical that you could just arbitrarily, I guess, put these nodes into different groups and then find the MST, but practically it's probably not the best way to do it. Yeah.
For a given cut, it's not necessary that the smallest edge in the graph is a part of the different spanning tree, right?
Sorry, can you repeat the question?
So for instance, if for any cut in the graph,
Yeah.
it's not necessary that one is a part of the minimum spanning tree for that particular cut, right?
The smallest crossing edge is going to be a part of the MST.
Okay. But
Yeah.
one is always not necessarily a crossing edge. Like if you
One-
have a different cut, then one might not be a crossing edge.
I think if you have a cut, you're always going to have a crossing edge. Is the thing.
But not necessarily one.
The value wouldn't necessarily.
Yeah, that's what I'm saying.
The value might not also be one. Yeah. It could be some other. Like it depends on how these nodes
A cut.
are displaced into those groups. Yeah.
Can you just Prim's algorithm?
Yeah.
Update instead.
Yeah, sure. Okay, cool. Okay. I'm gonna run through Prims just real quick. There's another one called Crucibles. It's in the slides. We won't have time to cover it, but you can always go back to the slides and revisit. Okay. So Prims, the idea is really similar to Dijkstra's. You know how Dijkstra's we're visiting all the nodes from the distance from the source? Prims is the exact same thing, except it only considers distance from the MST being built. Okay. So instead of just talking about words, I'm gonna walk you through this, I guess, the demo, just to kind of it'll be a better explanation of it. So the first thing that we have to do is we insert all the vertices into the priority queue or the fringe, right? So in this case, we're just going to arbitrarily start from the vertex A, but you could start from any vertex. But in this case, we're just going to pick A. So A's distance to value is 0, and then all the other vertices distance to values are infinity, and they get added into this fringe, right? Now we just kind of do the same thing that we did in Dijkstra's. We keep removing the vertex from the priority queue, and then we relax all the edges that point out from that current vertex that we're visiting, right? So in this case, we first have inserted A. Now we remove A, which is why it's covered in yellow, and now we have to relax all of its outgoing edges. In this case, there's one edge going to B, one edge going to D, and one edge going to C. So let's first look at this edge going to B. When we relax it in Dijkstra's, we say, okay, is the distance to value of the neighbor of B, is that greater than the distance at A plus the edge, right? But in Prims, we just ignore the distance of A, and we just, sorry, how do I better say it? For Prims, we only look at the edge, if that makes sense. So we say, okay, is the distance to value of B, is that greater than the edge of 3? Only the edge, okay? And in this case, B's distance to value is greater than the edge weight. So then we update its distance to value, we update its edge to point to the current vertex that we're on, and then we update the fringe to hold the value of 3 at the vertex B, okay? Then we do the same thing for C. We ask the same question. Okay, is the distance to value of D, infinity, is that greater than the edge of 2? It is, so we update the edge 2 value to A, and then update the fringe, right? So we keep doing this and so on and so forth. It's very mechanical until we get to this point, right? At this point, there's no more edges to consider. So then we actually just kind of rinse and repeat. We remove the next vertex from the fringe. At this point, it's going to be vertex C because that has the lowest value in that fringe. It's the value that's at the front of the priority queue. At this point, this is the thing about prims. Once you visit a vertex, you're doing two things. You're adding that vertex and that edge to your MST. And number two, you're actually making a new cut, right? So the first cut was actually this one right here. When we visit A, it's A is in one group, and then all these other nodes are in the second group, right? But when you visit a vertex, what you're doing is you're actually making another cut. So now this is the cut of the yellow is the MST that's being built. That's part of one group, right? And the second group is all the other vertices that we haven't visited yet. And then we just kind of do the exact same thing. We relax all the outgoing edges. And I guess the cool thing about it is all the dashed lines are the lines that we have already visited before. So Prims is actually keeping track of all the work that we've done already in the prior visitations of vertices. So in this case, we only have to look at the edge that's outgoing from C. And then we just ask, okay, is the distance to value at D, is that greater than the edge of 4? Once again, this is Prim, so we only considered the edge, not the edge plus the distance 2 of the current vertex. That would be Dijkstra's, right? So in this case, 7 is greater than 4. So then we update the distance 2 and the edge 2 values in the priority queue. And then we do that so on and so forth. You can walk through this demo on your own pace. But just for the sake of time, I'm just going to kind of speed through it. But eventually what you have once the fringe is all empty is you actually have this minimum spanning tree. Okay. Yeah.
But there's people who exclude the like total distance, but it still gives you the same output as Dijkstra, right? 6 is still less than 7, but it doesn't have to be. But how does it make it happen?
I think so. Sometimes you can run Dijkstra's on an arbitrary on a node, and it will give you the minimum spanning tree and the shortest path tree. But sometimes it won't. So it's like sometimes it'll give you the shortest path tree, and sometimes it won't. Like sometimes the MST and the shortest path tree are not the same. And yeah, but if you go back to the lecture that Hug gives, he'll show you yeah, you can find the MST if you run Dijkstra's on the right vertex, but not all graphs will give you the minimum spanning tree if you do it that way. Any other questions before we move on to the net? Okay.
We're going over time. I'm so sorry, guys. Can't cover heaps at the moment. It's past 9, so thank you all for coming. We'll upload the slides, send out the recording as well. Feel free to linger if you have any other questions. I'll be here for a bit, but good luck, everybody. Thank you. Thank you.
You're good. It's a hard one.